Hi and welcome. Today I'm over here at the lathe and I need to make a tool so that I can complete another project I'm working on that I've been working on for quite a long time. I'm interested in making a tool that will let me set a relatively accurate angle on my compound because I do not have a taper attachment, so that's the only way for me to do tapers. And this thing goes about 7 inches or something like that of throw, so that's pretty decent. You can do, small parts and get a decent taper. And a while ago, I came up with a solution where you take magnets and basically hold them, set magnets underneath and on top to set the angle you're interested in. So this is from an angle block set. Let me show you this. So this angle block set here, and currently it's set at about 30 degrees. And if I had an indicator on the ways here, and I take my cross slide back and forth longitudinally with an indicator, this shouldn't change in dimension when it's perfectly 30, at least as accurate as this gauge block is. Presumably the side of this is ground to match the dovetail inside so that the motion will follow the outside. I'm trusting that, so that's limiting accuracy right there. But the idea of having an angle block on here is a decent one. So a while ago I built this tool, which is just a magnet that sits on the side, and I can set my gauge block here. Then I can grab my indicator and just run along the side here, and all will be perfect, except for the fact that of a couple things. This design is not ideal. I realized after I made it that instead of putting a big magnet underneath here that holds it on, I should have had this piece extending over the top surface here much farther, with a couple magnets back here, and that would give it an excellent lever arm to support this. That's idea number one. Number two, I'm limited to the combination of angles I can do with my angle block set. So, this set comes with 1 degree, 2 degree, although this isn't big enough to stack a bunch of these together, so that's kind of limiting all by itself. And I was thinking to myself, hey, wouldn't it be nice to be able to do an arbitrary angle with something like a sine bar? So imagine if I made something that would hold a sine bar on here with a stack of gauge blocks, and I could do arbitrary angles and get fairly close to an accurate angle set. So that's where I'm going to go this week. I'm just sort of winging it. I'm going to have a steel plate that sits over the top of this guy and also extends out here a ways. That will allow me to set a sine bar up that I can run an indicator across, but that will also allow me to stack gauge blocks out here underneath it so that I can get a fairly accurate angle. And that's where I'm headed. I've been shooting this for a while. There is another way to do this, of course, that doesn't require any angle blocks at all, where you can also set arbitrary angles fairly accurately. And that solution is where you would put an indicator, and you need one indicator along the z-axis, which I'm calling this axis the z-axis, and another indicator across the y-axis or x-axis, which I'm calling this. And what that would allow you to do is, for every angle, you know that it's going to change by X amount of thousandths per inch of travel this way. So if you know that, you can just look at your indicator, move an inch on the DRO or your other indicator, measure, look at what the change is in this axis, and when it meets up, you're right on. And the farther you go, the better chance you have of being more accurate. So that is another solution that could work reasonably well. I just haven't, I've had sort of mixed luck with that because it depends very significantly on how that indicator ball rides along the surface. So you can have issues with getting accuracy that way as well. So anyways, my thought is, if you're just looking for zero change in depth, that's easier to do than looking for a specific number per inch, because that relies on you moving exactly an inch, and you get my point. So we're just going to give this a shot and see how this whole exercise works out. Well, as luck would have it, and not exactly luck, because I'm like a crow attracted to anything shiny, but I had picked up these pieces of Blanchard ground 4140 precipitation hardened steel a while ago, because the price was right. And I thought, boy, they're already pre-ground, so the two sides are fairly flat and parallel to each other. And what do you know? I think this will work out pretty good. So we just need to cut a piece off one of these and continue from there. They're a little over 6 inches wide, and I only need 5 inches, so that'll be perfect. And just got to figure out how much overhang on the compound I want and how much overhang outside the compound I want. Next stop, we're just going to hop on the bandsaw and cut off this piece. I'm just dimensioning the stock here, and I've biased the work so it's mostly to this side, so that when the cutter comes across, it's pushing more this way, even though it's still pushing a fair amount this way, but it's pushing, as you know, not as much this way, more this way. This cutter makes interesting chips. They're little tiny curly cues. Alrighty, so I've made some really rough layout lines because there's nothing really important dimensionally. The only surfaces that are critical are this flat edge here has to be vertical and perpendicular or parallel to this flat edge here. So this material's getting removed, this material's getting removed, and then I'm also going to remove a good chunk of material out of here as well, which I didn't actually draw on there, but yeah, so something like this material right here is also going away. This is going away. This is going away. And this is going away. And what that'll leave me with is basically a ledge that'll fit over the top of a vise. So this flat part here will fit flush down on, if this was the surface of my compound, it would fit on there. This part here will hold some magnets. And this part here will be the ledge where the sine bar is going to fit, and I can set my angles. So this is going to have a very generous overlap on top of the compound so that it'll hold nicely and solidly and not move around. So we're just going to take our time here, and we're just going to hog out a chunk of material, and then we'll run a finishing pass right along this edge to clean that up, because that's actually critical. And what I did discover is that I was trying to figure out why this was cutting so nicely. I go back to the eBay site where I bought this and look at the history, and the name has changed. So yes, the day before yesterday I looked, and it said 4140 pH on it. I went back yesterday, and guess what? It said it was, I forget the name of it. It's some free cutting steel that's resulfurized and had lead added for ease of cutting. And it's not really hardenable except with carburization, which I can't easily do at home. So now I'm out of luck. I'm just going to have soft steel, which I didn't want. I was going to harden the whole thing, the 4140, and then grind it. But I guess we won't be now. Somewhat bigger bite. This is a 3/4 inch fine roughing end mill, and that's taking at least a 1/2 inch width, 1/4 inch depth of cut, and it's having no issue with it at all. Of course, this is that nice cutting steel, so I guess what do you expect? At this rate, it should make quick work of it. Even bigger cut this time. Pretty close to the full width of the cutter, not quite. .500 RPM. So we've roughed it out. Now I'm going to pop on a finishing end mill, and I'm just going to get a nice straight line there and clean up the bottom. It's not perfectly flat. I got to really crank on that collet, or if I really cared about being accurate, I'd switch to one of these with a Weldon shank so that the end mill couldn't move any farther in. That's always a good idea. Alright, so I'm actually going a little bit deeper because it looks like it even slipped in the Weldon shank a little bit right here. So I'm going to go deeper in side mill. And I've locked my y-axis, so it should be fairly good. Now we flipped the part over, and the ledge I just cut out is over here. and I'm going to cut out the big chunk. This side is where the sine bar is going to go. It's a chunky bite right there. It's a little under 500 RPM and a fairly slow feed rate. And I'm only going about half the cutter, about 3/8 of an inch, 0.375. I don't know, was that worked out like 8 millimeters, something like that. I was roughing out this side of the ledge. This is where the sine bar is going to sit. But I forgot I also wanted to remove some material out of the top part just to lighten it up a little bit. It doesn't need to be as beefy as it is. This tool's already going to be really heavy. So I don't know if I can take this cut, but we're going to try. I'm just going to try it manually. Yeah, it looks like it's going okay. It's not as deep, it's about 1/4 inch. But as I reduce this little area right here, it's going to be weaker and weaker. So I thought I'd get this material out of there first before I take my finishing roughing pass over here and then finish it off completely, because there's nothing supporting this whole ledge. And actually, if I was smart, I would have cut out here first. I kind of did it backwards. That wasn't terribly bright. Almost done cutting the extra material on the top. I ran most of the time with a vacuum cleaner. Just going to chamfer the decorative parts a little bit. Next up, I'm going to take advantage of some ideas I stole from Tom Lipton in a project I did a little while ago, which is the drill and tapped screws. The 1/2-inch screws that hold the vice jaws on have been drilled and tapped to support 1024 screws. And actually I was kind of nutty when I did this, because I did 1024 on one side and 1032 on the other side, because I didn't remember what I did, which is just silly. But I made these 45 bracket holders here, and they'll hold 40 parts at 45 for me, which is what I'm going to be doing next. Is I am going to put relief in the corners here, so that if chip packing occurs, it won't offset the sine bar or the vise, the cross slide itself, because if you get chips in the corner and you don't have anywhere for them to go, it'll hold this at a weird angle. So we're just going to remove that possibility by relieving the corners. So I need to hold this at 45, and this is an excellent way to do it. And align these guys up with each other. Got these two 3/8 inch pins here, and this one, that hole, I got bored that hole poorly when I did it. There we go. Fortunately, the one on the other side is still pretty reasonable. And all this does is line these two up with each other nicely. So we want to machine out the relief in here. I don't know how well you can see this, but I've got a ball mill here. And my goal is to relieve the corner I don't know how well you're going to be able to see this, and I've just done it by eyeball, but we're going to give it a shot. We're going to need much higher RPM than we were using. A lot of stick out, so we got to go slowly. So here's the relief in the corner. I don't know if you can see it. It's pretty small. It's like a 16th radius kind of thing, or 0.0625. Just a tiny bit, just enough for chips to go. It's not like there's going to be a lot of chips here when I'm setting up, but you know, you've also got to deal with dirt and whatnot. So now I just need to flip it over and do the same thing on this side for the compound itself. Pull this off. To use an 1/8 inch end mill, I had to get an end mill extender, and I have them in a variety of sizes. I picked up a bunch of used ones, which got me a bunch of redundant ones, which I got rid of, but it's always the risk. But very, very handy to have, and sort of necessary if you want to use an 1/8 inch end mill, because if I put that in the collet would have rubbed before I could have gotten the end mill in there, or would have had to have a ton of stick out. So very handy tool to have. Alright, so I took this over the surface grinder and ground this nice and square and cleaned up the part where the sine bar is going to go. Of course, I had to accidentally bump the y-axis on the surface grinder with my knee, and just once. That's all it takes. Have to have an imperfection in every project I do, apparently. So next up, we're going to flip this guy upside down, and we're going to make some spaces for some magnets down here. Okay, so I've got some magnets here that are just a little bit over 3/4 inch, but it's okay because I'm going to bore out 1-inch holes for them so that I can epoxy them in from the sides. I think that'll work out better. Besides, with a magnet, you know, they create a circuit essentially, and you don't want the edges of the magnet touching a material like steel, because it'll shunt the flux lines right next to the magnet and right back into the sides. What you'd rather have it do is concentrate around the outside edge, so the flux lines are going to come out the top if that's north, and then go back into the steel and then to the back side. So I got to make sure the bottom of the magnet's touching the back side, because what makes magnets hold better is flux density. The denser the flux, the more they hold. So if I haven't got that wrong. So like I said, we're going to bore 1-inch holes, and we're going to put 4 of these guys down. They don't have a lot of work to do because there's not a lot of force pushing this way on this side of the plate, but they're just mostly to hold it on, because there's also a fair amount of weight and a lot of overlap, 3 inches of overlap over the compound. So we're going to do that next, and I'm going to center drill each one of these with a flat bottomed hole, 1/4 inch here. And I'm drilling these holes because I don't want the 1-inch end mill I'm going to use to do the flat bottom hole to have to fight cutting the center out. I think it's the first time I've ever used a drill bit in a collet before, but I already have the 1/4 inch collet in, so I just used it. I'm using a Weldon flat style end mill holder for this 1-inch end mill because it's so much more rigid. And to be honest, I bought one of these 1-inch R8 holders. This thing's ridiculous. These fins stick out so far because it's larger than the R8 at the top, and they're so thin that they don't hold the end mill hardly at all. This is basically a useless piece of crap. I would not recommend it to anyone at all for anything. Maybe cutting plastic. I take that back. So I drilled out the center of these magnet pockets with a 1-inch end mill. A brand new one, and it was chattering a bit, and I only had it at 240 RPM. I might have needed to slow it down just a little bit. Lesson learned. The other end mill I was using wasn't cutting a flat bottomed hole, it was cutting a conically bottomed hole, which was kind of bizarre. So I found a different one that's not in great shape, but it seems to be cutting a flatter bottomed hole. So I wanted the magnets to just barely be below the surface, so I'm using the edge of a scale that's in really good shape to check that out. Second hole I have to bore like 1/1000th or 1/1000th deeper. Guess a jig borer would be handy here if I had one. Another thing you'll notice, or may notice if you ever play with these, is that the magnet really wants to go to the edge of the pocket, even though there's a pretty big gap all the way around it. And the reason for that is what I was talking about, is that, and why you don't want a high permittivity or basically a magnetically conductive material around the outside of the magnet, is because you'll shunt the flux right into the side of the magnet. There's actually a fair amount of force. See, it wants to snap to the side. So in order to glue these in, I think I'm going to have to make some spacers to protect the side, to keep the magnet centered. So we might have to hop over to Lathe and make some of that real quick. So we're just facing off a piece of Delrin. We're going to make some spacers, and all these are going to, job of these is going to be to hold the magnet centered in the hole. So they don't have to be super precise. And they can even be a little sloppy in the hole, that'll be fine. So we're just going to take off 1/4 inch roughly. Beauty of plastic, especially Delrin, fantastic material to work with. This should be pretty close to what I'm looking for, which is just a tad over an inch. Yep. Now we're just going to bore out the middle. See if I got the size right. I want to make it a little bit loose. Oh, it's a really good fit. That's too good a fit. Matter of fact, now I might not be able to get that out. That's a really nice fit. Okay, I need to take another couple thousandths off after I figure out how to get that out. So here's the fit. It just slides in nicely. It's still a bit of a piston fit, which is probably a lot tighter than I needed, but we're going to go with that. Next step is I got to part off some 50 thousandths washers out of this stuff. Okay, now we're going to move over 50 thousandths, and we're just going to part this off. As long as we're here, we'll make a couple extras. Okay. Way more than we needed. Now I just need to deburr these guys. Look at that chunk of plastic that got wedged in there. Alrighty. So we made way more than we needed of these, but that'll be fine. Alrighty, so next up we're just going to glue these in with the spacers. And the whole point of these spacers is just to help align the magnet and keep it centered. And if you're wondering how I deburred them, it's got this little cheapo disposable scalpel, and I just rotated them around. Worked really well. Scalpels are really sharp. They're inexpensive. Worked pretty well. So I'm going to epoxy these in place. Now I made these holes a couple thousandths deeper than the edge of the magnet, because what I'm planning on doing after this, I'm just going to make a big mess, but is I am going to take this over to the surface grinder, and I am going to grind this whole surface here flat with the top of the magnet. They don't adhere themselves permanently beforehand. Yeah, so the only job of this little plastic bit here is to keep it aligned. And so next we're going to whip up a batch of epoxy, and we're just going to pot these guys in place. If you're wondering how to get all the little iron filings off of magnets, since you can only get so much with your hands, tape is the solution that I found works pretty well. And of course, when I go and surface grind these, that's going to be a little bit of a mess too, because all of the little filings that come off of the surface grinder are going to want to stick to the magnet, so that'll be a little bit challenging. But next up, I'm just going to fill this with epoxy, let it cure overnight, and then we'll come back. And I'm not going to use metal epoxy because I don't want to short out the magnet. Again, this is for maximum magnet strength. All right, so the epoxy's on. Now I just need to leave it cure. This 5-minute epoxy. It doesn't have to be particularly strong. I'm going to come back when it's cured, and I'm going to take a razor blade and remove the majority of it. Then, like I said, I'll take this over my surface grinder and get this thing pretty level with the magnet tops. And I'll square up this end at the same time. And I was stupid using even a stainless steel stirrer like this. The magnet was grabbing it. This mustn't be non-magnetic stainless. So I grabbed a large tie wrap, and that's what I used to spread it. Not ideal, but it worked. So we've ground the top side and the face where the sine bar is going to ride against. We also have ground the bottom now and the face that the compound is pushing up against. These magnets are pretty darn strong, so I got to let that down nicely, but it's not going anywhere. Alrighty, so let's start with a simple case. My compound is parallel to the axis of the lathe. Here's my chuck back here, and if you see running the indicator along the side of the compound, no movement on the dial indicator. So we are perfectly parallel. So now what if we want to put the compound at an angle? Well, of course I could use the angle marks over here to set that angle, but that would be very approximate. If we wanted to be a little bit better than that, let's try my new tool. All right. So let's say we want to set an angle of 30 degrees. How could we go about and do that? Well, first we're going to take advantage of a feature of geometry. So consider the motion of the cross slide along the longitudinal axis here going in this direction as one part of a parallel pair of lines. The other one is the center of the lathe chuck. Let's consider that another parallel line to this, and if they are not parallel, you've got a problem on your lathe. Now, when you turn the compound at an angle, let's say 20 degrees, like this, the compound is now cutting those parallel lines across like this. And we're going to take advantage of a feature that says that alternate angles from a line cutting two parallel lines are equal. So this angle is equal to this angle, and also this angle is equal to this angle. And the sum of these two angles is 180 degrees, of course, because that's a line. But that's not as important. We're going to take advantage of the fact that alternate angles are equal. So since now turning my compound is acting like this line cutting the axis across the center line of the lathe chuck and the travel of the cross slide, we can take advantage of the fact that when I turn this thing at this angle and I put an equal angle on the sine bar, that I should have a perfectly horizontal line here. And let's see if that works out. Alrighty, so one more thing before we move on. The sine bar is going to be sitting at the same angle that the compound's set at, but in an opposite side, basically the alternate opposite side of the line cutting through the two parallel lines. And so we're hoping the sine bar is going to end up just like this, parallel to the axis of the lathe, the longitudinal axis. And the height I need to stack the gauge blocks to get this proper angle depends on the length of the hypotenuse, which is 5 inches, or the length of the sine bar. And sine is equal to opposite over hypotenuse. Opposite, which is height, over hypotenuse. So 5 over h. I'm sorry, height over 5. So simplifying this, we multiply both sides by 5. It gets rid of 5 in the denominator here, and 5 times sine of the angle is equal to the height of the gauge block stack, and the angle in our case is going to be 20 degrees. So 5 sine 20 degrees is the height of the gauge block stack. I'm going to do that, and I'll be right back. All right, so now to set the angle, I've got my 1.7101 stack of gauge blocks here. I've got a can twist clamp just to hold the sine bar in place, although it really isn't going anywhere. And I've got my Noga arm here positioned just so it doesn't run into this the side of the platform. Now, if I'd made the platform bigger, I could do larger angles, but then you have to have a longer throw indicator. I really need a 2-inch throw indicator dial to do a good job on this. It'd also make it easier because I could set my zero at the pivot point of the whole compound, which would make everything great. Because right now I'm iterating much like the nod on a mill. You have to set this a very similar way. Here, let me rotate the indicator your direction a little bit. That might make it easier for you to see, because straight on. So in this case, I notice that as I move this direction, it's actually dropping. So the indicator to bring it back up and stop motion is this direction, but it's one of those iterative things now because I'm not at the pivot point for my zero. So what I tend to do is just bring it up a little bit, come back to just before the arm's going to touch, reset my zero, move down, see it's still dropping but a little less than last time, tap it back up, come back, make a new zero, and what you're really looking for is the rate of change to be almost nothing. And you can see I'm really close now. So we're just going to go a couple more thousandths of knock. Reset my zero, and we were almost there. It's a few tenths now, so let's just try a couple more thousandths. Looks like a couple thousandths are equal to a tenth or two. That might have been too much right there. So pick my new location, find my zero, and look, oh, it's starting to climb up. I overshot just a tiny bit. And there we go. Across like 2 inches, we have a tenth or two, which means this is really close to 20 degrees. So this tool is working out pretty well. I'm very happy about it because I have to, 20 degrees would be easy. I could just set an angle block on the other fixture I made that I showed earlier, which is just this really small guy. But the angle I need on the other one is 0.6 or 1.6 degrees or something like that, and without a sine bar you're really not pulling that off unless you've got a really interesting gauge set, or you make one particular gauge just for the project, which is another possibility. You head over to the surface grinder, set up your sine bar, grind a perfect angle gauge block, and then use that to set your zero. That's another option too. When your gauge stack starts to get small, like I'm actually considering this. So when the stack gets really small, your gauge block set won't be able to easily make that value anymore, especially if it's less than a tenth of an inch on the stack, because the smallest gauge block is 50 thousandths typically, but then the ones that have incremental changes all are by the 100 thousandths. And so if you need less than 100 thousandths, it's probably better just to make your own custom gauge blocks. What I probably will do is, machine a moderately accurate, within a couple thousandths height on a piece of bar stock, and then head over to the surface grinder and then grind it down and measure calipers until I get it right on, and use that to set my sine bar. So anyways, this has been a really interesting project, and I've needed this tool for a long time now, and I think it's going to work out really well for me. Give me feedback. Let me know what you think too, because I always like to hear feedback, and people often give me great advice on how I could have improved my design. So I'm always happy to hear it. Thanks for watching. Hope to see you next time.